Okay, we're going to talk about rational functions. We're going to go from the definition all the way to graphing. So the definition, let's look at the example first. So here's what a rational function looks like. A little easier to look at than this generic form. So of course you can pause if you need to. A polynomial in the numerator divided by a polynomial in the denominator. So obviously the denominator can't equal 0. If the numerator was 0, then the function would just be 0. So we're talking about a polynomial divided by a polynomial, and then also if the denominator is just a constant, you can just rewrite that as, a coefficient out front. You just got a polynomial function, not specifically a rational function. So you're going to see functions that look like this, and that's what we refer to as rational functions. So you're going to have positive whole number exponents. This is the polynomial, this is a polynomial. So of course we don't want 0 in the denominator, and for example, if this were just a 30 in the denominator, we wouldn't actually need to call that a rational function, because you could just factor out a 1 over 30 out front, and you'd just be looking at, in fact on this one, if you had a 1 over 30 out front of x squared minus 4x plus 4, you would just have a quadratic function. So finding intercepts for any function does not change. The y-intercept is f of 0. F of 0 I am a big fan of because it helps me, 0 helps me do arithmetic accurately. And for polynomials, you know that it's always just the constant that's left over after you plug in 0. So it looks like we're going to have 4 over 30, which is 2 over 15. So the ordered pair 0, 2 over 15 is on the graph. And now the x-intercepts, we can just set the numerator equal to 0, because if you set the entire thing equal to 0, the first thing you're going to do is multiply the denominator from the denominator over to the 0 on the other side of the equation. So you're still just going to end up with the numerator set equal to 0. For a rational function, you can just say this capital N of x is what I call the numerator. You can just skip straight to that and say, well, we're just going to set the numerator equal to 0, solve those, and we're going to get the x-intercept. So x squared minus 4x plus 4 factors into x minus 2, the quantity squared. So x equals 2 multiplicity 2. The behavior at this x-intercept we would say the graph touches and returns the same direction. So it does not cross the x-axis at this x-intercept. It touches and then returns. And that's the same thing as when we're learning polynomials. If the multiplicity of an x-intercept is even, the graph is going to touch and return. You can think about the graph of x squared. If the multiplicity is odd, it is going to cross the x-axis. So I'm just making a note so that way we can be reminded about multiplicity of x-intercepts. So found some intercepts of a rational function there. Okay, now on the graph of a rational function, and let me slide to page a little farther down here. On the graph of a rational function, you have a horizontal asymptote and you potentially have vertical asymptotes. So here's the graph of a rational function. I just want you to take a look at kind of how these, this is not a defined point. I'll get to this page in just a second. I just want you to take a look at how this graph works. So a VA is a vertical dashed line. The function is not going to cross that. And HA is where the graph flattens out as x approaches plus or minus infinity. So when I say HA, I mean horizontal asymptote. that gives us the end behavior of a rational function. So that's what we're going to take a look at. The horizontal asymptote describes the end behavior of the rational function, and the graph flattens out at the HA, so it's going to be a horizontal line, equation of a horizontal line. Flattens out at the HA as x approaches plus or minus infinity. So the first rule is if the degree of the denominator is strictly greater than the degree of the numerator, there's an HA at y equals 0 always. So if we take a look at this function, the degree of the denominator equals 4, which is greater than 2, which is the degree of the numerator. So this graph has an HA at y equals 0 by this rule. You'll learn more in calculus about why this works the way it does. So that's a nice one. Degree of the denominator greater than the degree of the numerator. The graph is always going to flatten out at the x-axis, y equals 0. So the next case is if the degree of the denominator and the degree of the numerator are equal. So let's take a look at this function right here. The degree of the denominator equals the degree of the numerator, and in this example it is 3. The HA, the rule is if that's the case, the HA is the horizontal line at the ratio of the leading coefficients. So the leading coefficient of the numerator is 12, leading coefficient of the denominator is 2, so the HA is going to occur at 6, and that's what this statement right here says. Now, there's another case, which we would call an oblique asymptote, which will specifically occur if the degree of the numerator is exactly 1 more than the degree of the denominator. So let's take a look at this example. The degree of the numerator is 2, the degree of the denominator is 1. So if that's the case, then we are going to have an oblique asymptote, which is a line y equals mx plus b where m is not 0. So just if you think about going back to graphing lines, a non-zero slope that is defined is not going to be a horizontal line. So that's why we call this either an oblique asymptote or a slant asymptote. And so we do this, we solve this, we find the equation of the oblique asymptote by doing the synthetic division of that polynomial, and then the y equals mx plus b without the remainder is the equation of that polynomial. So let's do the synthetic division here. Three comes straight down, 2 times 3 is 6, then we add straight down, repeat the process. So that's 4, looks like that's going to be negative 8, the remainder is going to be 10, but this is b, and then this is m. So the oblique asymptote is y equals 3x minus 4. You don't include the remainder. So let me show you here. Real quick. This is the graph of 3x squared minus 10x plus 18 over x minus 2, and then I put in the equation of the oblique asymptote here. So the blue is the rational function, and then the oblique asymptote, so the graph is asymptotic at y equals 3x minus 4. So here's what the function looks like without the oblique asymptote, and then if we just wanted to put that on there to show what's going on, this time it's purple. Rock and roll. Okay, however, a vertical asymptote comes from the factors of the denominator. So if you set the denominator equal to 0 and and solve for those x values aren't going to be in the domain. So if on this, this denominator x minus 1, if x minus 1 is the factor, we do not have a valid input of x equals 1. On the graph, we call that a vertical asymptote. So you set the denominator equal to 0. So this is a root in the denominator, in the polynomial in the denominator, so we still have to consider multiplicity. The multiplicity at x equals 1 is 2, since it's to the second power, and then the factor x plus 3, when we solve that, that would be x equals negative 3. As a multiplicity of 1, you do not need to write multiplicity 1. So this function, 1 over x minus 2, the quantity squared, times x plus 3, and that's in the denominator, also has VAs at x equals 1 and x equals negative 3. So on the graph, the function cannot cross these vertical lines. Otherwise we would be, causing division by 0. So the question is, what does the graph do at the VA? So keep in mind this multiplicity, even, multiplicity, odd. The behavior of the function at the VA, the graph goes the same direction if the multiplicity is even. So on either side you could shoot up, or you could both shoot down if the multiplicity is even at that VA. If the multiplicity is odd, they're going to go opposite directions. In order to determine, so let's say you know that the multiplicity is even, so it's going to go up on the left side, up on the right side of the VA, or it's going to go down on the left side and down on the right side of the VA. In order to determine what's going on when you're graphing it, with whether to pick this one or this one, you need to use the information around that VA on the graph, and you can always plot order pairs. So keep in mind that we had a even multiplicity VA at x equals 1, we had an odd multiplicity VA at x equals negative 3. So let's take a look at this graph. So here's the graph. Here's negative 3, so that it doesn't give you the vertical dashed line, but you can see that they're, what the graph is doing there. On the left side, the graph is going to shoot straight down. We have odd multiplicity at this VA. On the right side, the graph is going to shoot straight up. Let me put x equals negative 3 on that graph. So we're not super zoomed in. Those lines do not stack on top of each other, but the function cannot cross that VA. So that's odd multiplicity going opposite directions. Now if you look over here at x equals 1, so I'll just put that, I just graphed that VA, x equals 1. X equals 1 had an even multiplicity, so in this case, both are shooting upwards on either side. We knew that the graph was going to go the same direction because of even multiplicity. Now, a hole in the graph exists if there is a common factor in the numerator and denominator. So this is a function. Functions tell us about a relationship between the independent and dependent variable, x being the independent, y being the dependent. If this were, like an elementary algebra question or something like that, and it said just simplify the expression, you would then go forward and cancel out the x plus 6 and the numerator and denominator. We are talking about a function as the relationship between an independent and dependent variable. So if a function gives you an x plus 6 in the numerator and an x plus 6 in the denominator, you cannot cancel that out because you're losing an important piece of information. That important piece of information is negative 6 is not in the domain. So with that x plus 6 in the denominator, x equals negative 6 is not in the domain. However, it is also not a VA. So from the previous example, we saw VAs came from factors in the denominator. However, if you have the same factor in the numerator and the denominator, you are going to just have a discontinuity at that point. So you won't have a VA where the graph shoots down or up on either side. You're going to be graphing that curve, and at x equals -6, there will just be an open dot, a hole in the graph. So this is telling us that -6 is not allowed in the domain, and x equals -6 is also not a VA. However, there is a discontinuity, which we call a hole, in the graph at that point. So here's something where you would identify, if the question was, give any holes in the graph, x equals -6. Now, you don't want to write that as an ordered pair because -6 isn't in the domain, so it doesn't have a paired y value. So there is a hole at x equals -6 in that graph. Okay, before we graph that function, we're going to recall graph shifting techniques. Back in 2.6, we learned how to shift up, down, left, and right. We learned even and odd, reflect over the x-axis and y-axis. So here's just a basic rational function graph. It's a common one, 1 over x. 1 over x has this shape. It doesn't have a y-intercept because 0 is not in the domain, so you can't calculate f of 0. So there's no y-intercept. There's no x-intercept because the numerator can never equal 0. So this particular function does not have any intercepts. It does have an HA at y equals 0, and that comes from the property earlier about horizontal asymptotes. So it flattens out at y equals 0 at plus or minus infinity, and the denominator has a domain error at x equals 0. So there is a VA at x equals 0, which is the y-axis. That VA has an odd multiplicity. It's a multiplicity of 1, so that tells us that the arrows are going to go in opposite directions. Now, how would you determine what direction these arrows go? Well, pick an element in the domain, such as like -1, and you will get an output in the range. So if I plugged in -1, f of -1 is -1, well, that would tell me that this portion of the graph, is down here in quadrant 3. It's going to approach this VA. It's not going to cross that VA. Since the multiplicity at that VA is odd on the other side of the VA, it must have this arrow going up this direction. Now, if we took that same function and I said f of x minus 3, where x minus 3 is inside the parentheses, and then a plus 4 on the outside of the parentheses, recall from graph shifting properties, that is a shift right of this original function, 1 over x, and it is a shift up. So this exact shape, this exact graph gets shifted right by 3 and up by 4. So what we've graphed here is 1 over x minus 3 and then plus 4. So we have a right shift of 3, and this is not an ordered pair. I probably shouldn't have even put a dot there. I just wanted to make sure you guys could see it. That is not an ordered pair on the graph. I just wanted to show you that we shift right. Here's 3. What I should have done is just put a 3 there and put a 4 there. So now the VA is at x equals 3, still has odd multiplicity. Now the HA was shifted up from y equals 0 to y equals 4. And you would get the HA, you'd have to find to follow the rule that I presented to you earlier, get a common denominator, and write it as a single rational expression. Since this is shifted, what we're doing on this page is we're just using graph shifting techniques to graph 1 over x minus 3 and then plus 4. But we probably need to be able to just graph one from scratch. So let's take a look at this function. The y-intercept is f of 0, so let's do that real quick. F of 0 is 6 times 0 plus 4 squared over 0 minus 1 squared. So we're going to have 6 times 16 in the numerator, and then a positive 1 in the denominator, which is 96. Now let's go down here and do the x-intercept. Nah, we got room. Now let's do it right here. So the x-intercept, you set the numerator equal to 0 and solve. So x equals -4 with a multiplicity of 2. So that graph is going to touch and return the same direction at that x-intercept. So that's part B. Part C, the HA. So the degree of the numerator is 2. If you multiplied this out, you'd have 6x squared plus ... In the denominator, you'd have x squared plus ... So the degree of the numerator is 2, the degree of the denominator is 2. So the HA is at y equals 6 over 1, which is 6, from the rule that we talked about earlier. Now we have a single VA, and that comes from setting x minus 1 squared equal to 0. That's the denominator. So x equals 1 is a VA, and it has a multiplicity of 2. So it has an even multiplicity. And then the domain and range. So the domain excludes any roots of the polynomial in the denominator. So x cannot equal 1. Let's write that in interval notation. So negative infinity to 1, parentheses, union, and then we're going to union that 1 to infinity. Now, the range isn't as obvious without looking at the graph. So we are going to take a look at the graph and then see if we can figure out the range. So let's put all this information on a graph here. So the y-intercept was at 96. We have an x-intercept. This is not going to be drawn to scale. X-intercept at -4. And we have an HA at y equals 6. So I'll just put that on the graph. And we have a VA at x equals 1. Okay, looks like we can see that. So now we need to determine, first of all, we've got the end behavior. We know it's going to flatten out. At the VA, we have even multiplicity. So one thing I want to mention, and it's going to pop up on this question, is that the horizontal asymptote, keep in mind, it gives you a description of the end behavior. If you cross an HA that doesn't violate any rules of math, such as division by 0, it tells you what's going on as the graph approaches plus or minus infinity. However, the graph cannot cross the VA at x equals 1. So we do know that we have to touch this x-intercept, and this x-intercept has even multiplicity. So this x-intercept is going to touch and return the same direction. The next important piece of information is that it goes to a y-intercept at 96. So we know that this graph has to go from -4, 0 on the x to 0, 96 on the y. It doesn't turn around. It can't turn around and go back here because there's no x-intercept. Now, as x approaches negative infinity, we know it's going to flatten out at y equals 6. At this VA, x equals 1, the graph, the VA has even multiplicity, so on either side of the VA, the graph is goes the same direction. So it's going to be up on the left. Since we know it's going up on the left, it has to go up on the right, and the graph is going to flatten out and approach y equals 6 as x approaches positive infinity. So from this information, so for example, the y-intercept's not down here, you know, the graph doesn't go this way, it doesn't go down to negative infinity on the y or anything like that. Kind of putting the pieces of the puzzle together, we can look at this along with the previous page and determine the range. The range is defined at y equals 0 and it goes up to infinity. So the range is not necessarily as straightforward of a calculation as the domain. The domain, we just set the denominator equal to 0. Any x values that cause division by 0, we take those out of the number line, boom, you've got the domain. The range might need a little bit more critical thinking behind it, but we have this least value right here at y equals 0, and these arrows have to go up. They're not going to cross the VA, but they are going to approach infinity on the y-axis. Okay, that's rational functions.